All right, we got to talk here because we had a situation. Things do not always have constant velocity. Sometimes, like that dry ice puck on a ramp, sometimes they accelerate. So let's make sure we know what we mean when we talk about acceleration. So acceleration, and again, we're in chapter 2 here, so we're just talking about one dimension, things that can only move back and forth in a straight line. So constant acceleration. What is acceleration? Acceleration is the rate of change of velocity. So what does that mean? Well, we can talk about like slopes and things like that, but we have the language of calculus now to talk about. So that's even a little bit better for us. So acceleration is equal to the rate of change of velocity with respect to time. So if your velocity is changing, well, maybe it's increasing, then this would be positive. Maybe it's decreasing, this would be a negative number. And of course, since velocity is equal to the rate that your position is changing, that also means that acceleration is dv dt, and since the velocity is dx dt, then acceleration is also the second derivative of position. Hey, how about that? So a couple things to say about this. For constant acceleration, what would the graphs of position and velocity and acceleration versus time look like? Well, there's some different things that they could look like, but let's start with, let's do this. Let's make a position versus time graph. This is an x versus t. Let's make a velocity versus time graph. And then let's make an acceleration versus time graph. Now the easiest one of these to make, if we're talking about constant acceleration, well then the acceleration graph is just a constant. Now this, if the velocity is changing at a constant rate, that means the velocity must be linear, because the slope of this is at the rate that it's changing. The slope of this is the rate that it's changing at, which is a. The slope of this is equal to a, and that's this constant. So maybe this has a slope of 2, then this would be a horizontal line of 2, right? And now, what about the position versus time? What would that look like if you have constant acceleration? Well, we know, just recently you learned the power rule in calculus, so if this is like successive derivatives, if this is like a 0th degree, if this is horizontal, a constant's like a 0 degree thing, and this is a linear graph here, so that's like 1st degree, then this must be 2nd degree. So this would have to be some kind of parabola. So the slope of this, for example, the slope of this starts out at 0, and then the slope is some positive number, and it's some bigger positive number. This is that graph of those slopes. It starts at 0, now it's some positive number, now it's bigger, and so on. All right, so this sure does have everything to do with calculus. Okay. Now, they don't have to be, for example, this doesn't have to start at the origin, this does not have to, this could have a negative slope, so there are different examples of these, but it is always the case if we have constant acceleration, position time will be linear, not linear, this will be linear, got ahead of myself, and this will be quadratic, and this is constant. So that will always be true, and they have to agree with each other. But this could be like a different piece of a quadratic, could be opening down. This could be a positive or negative slope, and it could start anywhere. And this could be some horizontal line in positive or negative territory. All right, cool. So what else to say about this then? Well, we can make some equations that we're going to call the kinematics equations. I'm going to do a little bit of work, and then at the end of all this, I'll summarize them and write them all down for you. I'm going to start with looking at let me title this section here so it's clearer in your notes. Sorry, we should call this deriving the kinematics equations. And I'll tell you right now that those kinematics equations you can use when you have constant acceleration. You cannot use them if you don't have constant acceleration. So here's a generic velocity versus time graph with, of course, constant acceleration. So let's see, maybe it looks like, I'm not going to start it at 0 because I want it to be a little bit more generic. Let's call this our initial velocity, v sub 0, and let's say it has some slope, and of course that slope is the acceleration. Well, what's the equation for this? The equation for this line, this is v versus t, would be v as a function of time is equal to the slope a times t plus the intercept. I'm thinking just y equals mx plus b as I'm going through this. That's like my y equals, that's my slope, that's my horizontal axis variable, and then my intercept is that. Okay, and then at some time t, which we could consider like some, like t1, I guess, at time t1, we'll say that it has velocity v1. And often we see this as this sort of like final. This is a beginning, an initial, and a final. So we often see this written in this form. And the sub-0 means time 0, so initial, that could be time 0 also. These are just interchangeable versions of this same idea. So that's v1, and this is v sub 0, and this is vf, vi, just two different ways of describing a starting time and an ending time, right? Or two times that you're interested in. Okay, so this is a useful equation here. And you might be thinking to yourself, that's kind of like my final position is equal to constant velocity times t plus initial position. You might be thinking that it's kind of like that, and it is kind of like that, except this is for constant velocity. Because if you have constant velocity, then your position time graph is linear. All right, so now we have constant acceleration. So let's see, what else can we do here? Well, there's another thing that we could do. I'm going to recopy this graph so I don't mess up that pretty version of it there. just another version of the same generic constant acceleration. I want you to notice here, let's say this is my ending time here, so let's call this here VF. And maybe I'll call this VI to be consistent with the initial final. So here's my initial velocity, here's my final velocity. What's the average velocity here? Well, the average velocity here, since this is linear, is going to be the average of the velocities. That's not always true. If you had some kind of bendy velocity graph, then it's not true that you can just average these. But if it's changing in a nice, steady, linear fashion, then I think it should be pretty clear that the average velocity right here is going to be right in between those two. So, excuse me, I'm going to write that if I just take those two and average them, that's how you average two numbers, right? You add them together and divide by 2, that is equal to average velocity. But we also know from just the definition of what average velocity is your displacement divided by time. That's a definition of what average velocity is. Right? You have that in your notes from earlier this chapter. So if this equals this and that equals that, then by the transitive property of equality, this must equal that. So let's cut out the middleman here and do that. So delta x over time is equal to VI plus VF over 2 times, oh, sorry, just that. I'm getting ahead of myself. I'm going to do a little algebra now. I'm going to move that time up here, and I'm going to move the 1/2 out to the front, so it's going to look slightly different, but I'm going to write it like this. So I'm going to move the time over there, take the 1/2 out to the front, because I can do algebra 1. And that gets me, oops, I was down there. There it is. That gets me another equation. How about that? Okay, now more algebra. Let's see if I can do this without messing it up. All right, so I got an idea. So far, I have two equations. I'm just going to rewrite them here. I've got VF is equal to acceleration times time plus initial velocity. Did I say final velocity there? I feel like I said the wrong thing there. Final velocity is equal to acceleration times time plus initial velocity. That's the right thing. Maybe I said it twice. That's okay. And then I have this other equation that we just got a minute ago. And there's a couple of things that we can do here. Like, for example, notice that here there's no a in this equation, and there's no delta x in this equation. So we might think that we could do some algebra and combine these somehow to yield something new. And we can, and I'll show you right now what we're going to do first. So I'm going to solve this one for t. So if I subtract vi to the other side, and then divide by a. A little more algebra 1 for you. And then I'm going to substitute over here, delta x is equal to 1/2 vi plus VF, but instead of putting a t here, I'm going to substitute this expression. If you're wondering to yourself, are you ever going to have to derive these yourself? The answer is no, but I will try to avoid at all costs, I will try to avoid ever just handing you an equation and saying, hey, take my word for it. I don't think that's a good idea to to do that, ever. So let's see where this ends us up. I think that probably I don't want to have this a on the bottom here. So I think I'm going to multiply both sides by a. That'll move that over there. And then I think also I'm going to multiply by 2 to get rid of that. So by multiplying both sides of this equation by 2 and by a, need to move, get rid of those denominators. And then all that's left over there is the difference of two squares factored out here. So that's VF squared minus VI squared. And then the way we usually see this equation written, this just gets added over to the other side. So there's another equation. Cool. And there's one more that I want to get for you. Let's see if I can remember how I need to combine things to get it. I want the equation that's missing VF. So let's see if I can get it this way. So I'm going to go back to these two equations here, but instead I'm going to take this delta x is equal to 1/2 VI plus VF times t, and I'm going to substitute this. Alright, so let's do that and then do some more algebra. So delta x is equal to 1/2 VI plus, so instead of VF, I'm going to write AT plus VI times t. Okay, and let's see, do some simplifying here. So here, I'm going to just do all these steps at once because, you know, you guys are grown-ups and you know how to do algebra. So this t is going to distribute to all these terms, and the 1/2 is also. So I'm going to take this one, at, and then there's another t, so that's going to be at squared, and then there's a 1/2 there. So that's 1/2 at squared. And then, let's see, I've got 2 VI's here, but that's being multiplied by 1/2. So 1/2 times 2 VI is just VI, and then I'm also multiplying by t. And there's another equation. And this one also, if you think of delta x as being like your current position minus your, oops, that's a V, minus your starting position, you could think of that as your sort of ongoing delta x, then this could be rewritten as the position function x of t is equal to 1/2 at squared plus VIT plus your starting position. Don't know why I keep wanting to write a V there. So these are really identical, right? It's just that when you have your delta x, that's like starting minus final minus initial. We just peeled off the minus initial and added it over here. That's all. But if you wanted to have a real-time graph of your position in a situation like this where you have constant acceleration, that's what you would need right there. All right, so summary. Oh, there's some stuff on that sheet. There's a blank one. And you can ignore that number 28 right there. So in summary, the so-called kinematics equations, which are for constant acceleration only. Like right now, we don't know a whole lot of different kind of physics situations. to try to deal with, but down the road things are going to open up for us and we'll have situations where there is not constant acceleration, and many a physics student has made the mistake of trotting out these kinematics equations when they are not appropriate. So they are for constant acceleration only. All right, what are they? Well, let's see. I'm going to write them in this order. Of course, the order doesn't really matter. And this one, well, let me write them all out and then I'll make some notes around them. So then how about VF is equal to AT plus VI. That's just that equation for this straight line when your velocity is changing at a constant rate. That's the slope. There's your horizontal variable, and there's your intercept. Then we have this one. Then we have the one that's really, it comes right from the definition of average velocity, where we know that delta x is also equal to your average velocity times time. This is average velocity, this is time. Of course, this is only average velocity in this situation where you have constant acceleration. All right, so some observations about these. These two this is like a position versus time graph, and we can see now that that's going to be quadratic always. We already discussed that before. We knew that that was going to be the case. And then here, this is like my velocity as a function of time. This is like your velocity as a function of time. So when we graph these, if we're going to graph things as a function of time, these are the two that we graph. What about these, you say? Well, this one doesn't have, I mean, what are you going to use? What's going to be your horizontal? I guess you could do VF squared. I don't know. It's just not, it's not really set up to be something that we're going to graph. And likewise here, because in this one, your velocity is going to be changing, and so is your time, right? As time ticks by and you're looking at the velocity at that time, you have two different things that are changing here. So that's not going to work on a two-dimensional graph. So these are the two that we often graph here, and that's why I put those first. All right, how many different variables are there that show up in these equations? There's delta x, let's see, that says 1, 2, 3, 4, I already counted time, but then there's also VF, and then that's all. So all of these equations are some combination of 5 different physical quantities. And notice that each one of these equations uses 4 out of those 5. So sometimes when you're doing a problem and you're looking at these equations and trying to figure out which one it is you should use, it's good to know what's missing from each of these equations. So what's missing here? Well, let's see. This is missing VF. Final velocity is not part of this equation. So if you have a situation, a problem where you don't know what the final velocity is, and that's also not what you're looking for, then that's your equation you should be using right there. What's this missing? This is missing displacement. This is missing time. And this one is missing acceleration. Now, if you like things in this world to be as symmetrical and predictable as possible, which a lot of us do, you might be wondering to yourself right now, wait a second, there was 5 variables. Where's the equation that's missing VI? And I'll tell you right now, the equation that's missing VI looks just like this one, except that this is a minus sign right here, and this is a VF. and we rarely use that, and I don't want to clutter up your notes in your mind with that extra one. So it looks a lot like this. I think it makes things more confusing to have it in there. We're going to stick with these 4. Those are the kinematics equations. There really are 5, but we're just going with these 4. So how do you use them? Let me give you a quick example. Let's say you have a situation car accelerates uniformly. What does that mean? If it accelerates uniformly, that is just code for constant acceleration. So that means we can use these. A car accelerates uniformly from rest to 25 meters per second. That's about 50 miles an hour-ish. You can double meters per second. Gives you a good ballpark on miles per hour. So it accelerates from rest to 25 meters per second on a 100-meter track. So in other words, it starts at rest at the beginning of that 100-meter track, and then it's going 25 meters per second at the end of the 100 meters. I think that's a pretty short distance to accelerate that much. Just guessing, just making these numbers up. So what is the acceleration? What is the acceleration? Let's make that part A of this question. Well, okay, let's see what we got here. Which of these quantities do we have? Here's what I suggest that you do when you run into a problem like this, a uniform acceleration problem, and you feel like you should be using the kinematics equations. Make a list of the quantities that show up here. And you should probably pick an order so you're consistent. Delta x, A, VI, VF, and T. That's the order I'm going to write them down in. So what we're hoping is we are going to be able to play this game successfully if we know 3 of these things. Then we should be able to find whatever 4th one by picking the right equation. So let's see what we know here. Do we know what delta x is? Delta x is the displacement of this. Do we know how far? Yes. Started at the beginning of the track, ended at the end. It's a 100-meter track. Do I know what the acceleration is? No, but I might note here that that's the thing I'm looking for. Do I know what the initial velocity is? Well, there's only one other number in this problem, and that's it went from this to that, so that must be the final. And you just have to watch out. If you find yourself in a situation where it seems like you're missing something, there's another piece of information that you need, watch out for things that are 0. You might not see the number 0 here. Well, you don't see the number 0 because it's not there. But from rest means an initial velocity of 0. Right? So I have 3 quantities, and I'm looking for this 4th one. So notice that in this particular problem, time is the thing that I don't know, and I'm not looking for it either. So I'm going to go up here, and I'm going to look for the equation that's missing time. That's this one. And before I start plugging numbers in, I'm going to write down the equation that I'm going to use. For those of you who are lazy about things, you're like, what? I got to write down the equation without plugging anything in? Yes. Sorry. Now here I'm going to let you, some physics teachers of the world may object to this practice, but once we start plugging things in to keep our equation nice and neat, I'll let you leave units off. We will have to reintroduce units when we report our answer. All right, so it looks like my acceleration is 25 squared over 2 times 100, which .125, and seems like 2 sig figs is a reasonable way to report that. Now, we didn't talk about the units here for acceleration, so let's just take a second to do that. What does this mean, meters per second squared? Well, let me just flip back to this graph. Here, the slope of this line, if this is what acceleration is, if acceleration is the slope of this, well, in SI units, velocity would be meters per second, and time would be seconds. So the slope of that is rise over run, and that's rise meters over seconds. So really, when we see this, meters per second squared, that's just kind of a shorthand way of writing that. Really what's happening is, for every 1 second that goes by, my velocity is increasing, because this is positive, by 3.1 meters per second. And we often write that like this because, I don't know, I guess we think that looks too messy or something. But that's really what's going on. Every second that goes by, you're having a change in your velocity. And then we allow ourselves to do the algebra here, treating these like they're little variables and putting the second squared on the bottom. All right. And then I said there was going to be another part of this. So real quick, what if instead of looking for acceleration, what if we were looking for time? So how long does this take for this car to do this? Well, let's see. If we were doing that, then acceleration would be the thing that we didn't care about, although we do have that now. I'm going to redo it like we're doing that from the start. So which equation is missing A? It's this one. I'm going to write down that equation before I start plugging things in. And let's see. Delta x is 100 equals 1/2 times VI is 0. Final velocity is 25 times time. So, my handy calculator, I think that's not so much after all. I thought it was going to get down there a little less time than that, but nope. So there you go. That's going to take 8 seconds for that to happen. And that is all for right now. Those are your kinematics equations. Very useful.